بسم الله الرحمن الرحيم. So very quickly, regarding this comment, last time we talked about combining the Shannon capacity with the Nyquist theory, and we talked about this example where we calculate first the capacity of the channel based on certain signal to noise ratio. And as we mentioned before, this is the best case scenario. This is the theoretical limit that we can get on the channel. It doesn't mean that in practice we can get that. So as a designer, as a network designer, if you want to design certain signaling scheme, you cannot use this limit for design. So instead, this 4 megabits per second is less than the 6 megabits per second, which is the theoretical capacity. So we have to reduce the typical actual throughput or the actual rate that we can get on the channel below the theoretical limit. So based on that, we use the Nyquist theory to calculate the number of levels. So this number of levels, if we increase it more than that, this means that the actual data rate that we will use on the channel is more than 4. And if we increase it more than 4, you may not be able to get it through this channel because the theoretical limit is 6. So if you increase it above this, actually maybe 4 megabits per second might also be not achievable over this channel, as we will see later. So there's a big difference between the theoretical bandwidth or the bandwidth or the limit of the channel and the throughput or the actual data rate that you can get. لا 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 لا. Yeah, well, it's based on some estimate. In the exam, if I were to give an exercise, I have to give you some hint. I will not leave it to you to assume. So there's no actual relationship. Okay, so I have to give you that مثلا throughput is 2/3 the actual capacity. So the typical data rate is 2/3 the theoretical capacity or something like that. So I have to make it quantifiable for you. So today's topic is about a very important metrics, and this is very important because most of you are going to measure this as part of the project. So as part of the course project, we need to do these measurements and we need to understand what they mean exactly. So, so these measurements or these metrics are used for performance evaluation. So we need to measure the performance of transmission over a particular channel. So first, we need to know the actual bandwidth or the theoretical bandwidth. We need to estimate the actual throughput. So the bandwidth gives you the best case scenario, and the throughput gives you the actual data rate that you typically get over this channel. For example, all of us, maybe we have plans, مثلا with Uridu, we have a plan of like 10 megabits per second. But have you ever checked the actual data rate that you get? Sometimes it's 1 megabits per second or 2 maximum. So you can never get this 10 megabits per second by any means. Because this 10 megabits per second is the best case scenario as theoretical limit, and it's based on certain properties of the cable without taking into consideration any noise, any loss over the line, any impairment of the line or any cut or anything. And also doesn't take into consideration the protocol overhead and all of this. So the actual throughput that you get is typically significantly less than the bandwidth. Latency is also a very important metric that we need to understand, and it has different components. And at the end, we talk about bandwidth delay in sequence. So the bandwidth, when we talk about bandwidth in hertz, this is what we have been measuring since the beginning of the course, and we said that we can get the minimum bandwidth using Nyquist theory, right? in hertz based on using one harmonic, and then Nyquist generalized that and so on. So the bandwidth in hertz refers to the range of frequencies contained in the composite signal, or in other words, if you look at it from the channel point of view, this is the range of frequencies that the channel can carry or the channel can support. So if you have a composite signal, this composite signal has range of frequencies, so you see the minimum and the maximum range, and this will be your bandwidth. If you look at it from the channel point of view, you see what is the minimum frequency that the channel can support, what is the maximum frequency, and also this is the bandwidth. Sometimes we measure the bandwidth in bits per second, and in that case we refer to the number of bits per second that the channel or a link can transmit, which is basically, again, it's proportional to the bandwidth in hertz. So we know that n equals double the bandwidth for one level, or in other words, for one bit. So not one level, two levels, or representing one bit. So basically, the bit rate equals to the double the bandwidth. And again, this bit rate is theoretical. It doesn't mean that you will get this in reality. In reality, you will get much less than that. So this is the bandwidth. So the bandwidth of a subscriber line, this is an exercise. So the bandwidth of a subscriber line is 4 kilohertz. So this is the actual bandwidth of the channel itself. So the bandwidth of this line for data transmission can be up to 56,000 bits per second. How many levels did I use here? Someone calculates it and give us the answer. All right, so so basically, this is calculating again the bandwidth in bits per second based directly on the actual bandwidth of the channel. So if I were to use Nyquist here, I can use certain number of levels to achieve this bit rate. But again, this bit rate is theoretical. So if that telephone line improves the quality of the telephone company improves the quality of the line and increases the bandwidth to 8 kilobits per second, so we know that the theoretical rate is proportional to that bandwidth. So the bandwidth doubled, so the theoretical rate will also double. So the theoretical rate will become 112 kilobits per second. Okay, because we said that the theoretical bit rate is proportional to two things: proportional to the bandwidth and proportional to the number of levels that we can use. But of course, the number of levels is proportional to the logarithm of the number of levels. So how many levels? 7, probably 7. All right. So the throughput. The throughput is the measure of how fast we can actually send data on the line, which is less than the theoretical limit. It's significantly less than the theoretical limit. And it can be due to slower speed at the transmission, because in some way, what we assume is that this transmission line is idealistic. The speed of the signal on this transmission line is the speed of light. There's no noise, nothing. So this is an idealistic case. So at the transmission ends to handle the data carried on the transmission. Okay, so if a network with a bandwidth 10 megabits per second can pass only an average of 12,000 frames, and each frame carrying an average of 10 kilobits. So we can simply calculate the number of bits per second, right, by multiplying the number of frames times the size of the frame, because we know that it's per minute, so we divide also by 60. So when we divide by 60, the actual bit rate that you can get is 2 megabits per second, which is significantly less than the 10 megabits per second. So the 2 megabits per second is 1/5 the bandwidth. And that's typically what you can get in reality. So the overhead and the reduction in the throughput compared to the bandwidth is sometimes 80% or 70%. Okay. So any questions so far? So this is the difference between the bandwidth, which is the theoretical limit, versus the throughput, which is the actual measure of data that you can send over the channel. So so in your course projects, you can simply calculate, or you can get the bandwidth, the theoretical bandwidth, because it's part of the specs, or it's part of the technology that you are using. For example, you know that you are using 802.11b. So the maximum theoretical bit rate on this type of technology is 11 megabits per second, for example, or I don't know, 11 megabits per second. So this is the theoretical bit rate that you can use. But you can calculate the throughput by transmitting an actual traffic and try to increase this traffic gradually, like what TCP does. Try to increase that traffic rate gradually and see what is the maximum rate that you can get actually on this channel. And the way you measure the throughput is simply by looking at the receiver side and say, how many bits did I receive in 1 second? So you have 1 second window, and then you move this window 1 second across the time. So between this window, how many bits did I receive over the receiver? So the number of bits that you receive in 1 second window, this is the actual throughput, or the average throughput. And then what you will notice is that this throughput is not fixed. The throughput is also not fixed, because again, we have some dynamic environment, so there are some changes that happen to the environment. Especially if you're using wireless. If somebody is passing by the corridor, he or she affects the throughput somehow, because he affects the signal, the wireless signal. Okay, but even on the cable, because of the induced noise and because of the other types of noises that we have studied, also the throughput changes slightly. Okay. The delay is a more complicated issue because the packet itself, or any bit, when it transfers over the line, it actually encounters multiple components of latency or multiple components of delay. So we need to understand all these components. So I'm not sure if that will work now. No. All right. So if we assume that we have the transmitter, so this is the sender. So at the beginning, you are trying to send some packet or any data stream of bits. So at the beginning, the transmitter is trying to send that over the channel. So the channel is going to the receiver. Okay. So there are multiple components of latency that affects this this packet or this stream of bits. So there is what we call the transmission time. Transmission time talks about the time that the message takes to get on the transmission medium, which means that from this point, I want to get this packet on the transmission medium completely. Okay? So the time that the sender will take to start sending this one bit until the sender finishes sending this bit over the line, this is what we call transmission time. And this transmission time is based on two components, simply. It's based on the message size and the bandwidth. The bandwidth, you can think of it as the thickness of the pipe, where the pipe is actually the transmission medium. Okay? So if this pipe is thick enough, I can transmit the packet much faster. Okay, so the flow can be faster. So the transmission time, this transmission time, in terms of time, is actually the size divided by the bandwidth. Okay? But that's not the only delay component that the signal or the packet encounters. There are some other components. So the packet, when it's on the line, it's converted into a signal, right? Whether it's in the baseband or broadband. So now the packet is a signal. So the time that the sender takes to convert the packet to a signal and finishes putting it on the line, this is the transmission time. Okay? So after that, the signal travels, or what we say, propagates through the transmission line. So the propagation delay is based not on the size and the bandwidth in that case. It's based on the speed, right? So it's based on the speed. So it's the time is basically distance over speed. So in that case, the propagation delay will be the distance between the transmitter and the receiver divided by the speed. And here, the speed, ideally, it's the speed of light. However, the typical speed is less than the speed of light slightly. Okay, so this is the second component, or the propagation delay. The third component, which is typically in the internet and in any transmission system, you have some intermediate devices, right? So it's like a switch, a router, or something like this, right? So when the packet, when it leaves the sender, it passes through some network devices. When it goes through these network devices, the packet, like for a switch, if we were to assume that there is a switch in the middle, sometimes there are more than one switch, right? So for each switch, the frame will be stored in the memory and will be processed and then will be put again over the line, right? Because it's not, live is not only a transmitter and a receiver and that's it. So there are, multiple nodes connected to each other. So the switch needs to take this frame and switch it to another line and so on. The router needs to do the same thing. So in processing this packet, there is a queuing delay. So the packet or the frame will be put in some queue, and then I will have to process this packet on first come, first served basis. So it's like when you go into a bank and you need to do some process, so you have to stand in a line. It doesn't happen that all the time when you go, you see no one and you get the access to the teller right away. And even if you get access to the teller, also the teller needs to spend some time, which is what we call the processing delay. So the minimum that you will get is what we call a queuing time. Queuing time. And this time is based on how crowded the transmission line is. So you may have to wait for a short time, a long time, depending on the load on this transmission line. So this queuing delay, in that case, is variable because it's dynamic. It's based on how many person in the queue, right? And that changes over the time. So it's not like the propagation delay or the transmission delay. It does not have a specific equation. Okay, so in your course project, you can sort of ignore the queuing delay, but that's not accurate, right? But sometimes the queuing time or the queuing delay is very tricky to calculate. So that's why sometimes in experiments, what we do is that we take the timestamp when we start sending the packet. We take the timestamp at the end until it reaches the receiver, and then the total delay, we calculate the total delay. If we have some estimate on the transmission delay and the propagation delay, then we can subtract it from the total delay and get sort of the queuing time. And that queuing time or queuing delay changes over time. It's not something fixed. All right. So we have the queuing time, transmission time, and propagation time. Any question? These definitions need to be very clear in your mind. So this is this exercise talks about how to calculate the propagation time. So what is the propagation time? If the distance between 2 points, transmitter and a receiver, is 12 kilometers, and assume the propagation speed is 2.4. We know that the speed of light is 3 times 8 to the power 8, 10 to the power 8. So the typical speed, the typical propagation speed over the propagation line, or sorry, the transmission line, is typically less than the speed of light, and it depends on so many things. Okay. In any case, if so, we know that we can calculate it. We can calculate the propagation time by the distance divided by the speed. And again, watch for the units. Watch carefully for the units. So we have to calculate the value, okay, and unify the units to make it meter per second or meter per, I don't know, or kilometer per second or something like this. Watch for the units. So the example here shows that a bit can go over the Atlantic Ocean, which is this total distance, in like 50 milliseconds. Okay, so that's so if you were to have like a submarine cable under the ocean, the typical speed is like in the 20,000 kilometers, 12,000 kilometers, and if you were to use this propagation speed, then typically the 1 bit will spend like 50 milliseconds to go through the transmission line. Of course, it's not that trivial because you have lots of intermediate devices that have to process this frame in the middle. So it's slightly more than 50 milliseconds. So we can calculate the total delay, which is composed of the transmission delay and the propagation delay. So if the propagation time and transmission, calculate the propagation time and transmission time for a 2.5 kilobyte message. So the 2.5 is the size of the packet itself. So that also that of course refers to which type of delay? Transmission delay, because in the propagation delay we don't need the size of the message, because it's not a message anymore, it's a signal. Propagation delay deals with signals, not a message with a specific size. So the bandwidth of the network is 1 gigabits per second. So 1 gigabits is 1 times 10 to the power 9. So we need to watch for the unit. Assume that the distance between the sender and the receiver is 12,000 kilometers, and that the light travels at 2.4, or the signal itself travels with a speed 2.4. So from these 4 components, we can simply calculate the propagation time, distance divided by the speed, transmission time, size divided by the bandwidth. So that's the total delay. If we were to ignore the queuing delay, assuming that there are no intermediate devices in the middle between the transmitter and the receiver, it's just a simple communication system, then the total delay will be the summation of these 2 values. Okay? So we can see from here that each of these components can be the predominant component. Yani, sometimes the propagation speed, or the propagation delay is much more than the transmission delay. And this is typically if we're talking about submarine cable and the distance is huge. Okay, so if the distance is huge, then the propagation time is more significant than the transmission time, especially if the channel or the cable itself has very high bandwidth. But sometimes it's the other way around. Sometimes the cable itself has low bandwidth, and we're talking about short distance. If we're talking about short distance, which is typically what you would have in any project, you need to do some experiment for a short distance. For a short distance, you need to send from one transmitter to one receiver in a short distance. So in that case, typically the transmission time will be more significant than the propagation time. Okay? In some cases, especially for short transmission, we ignore the propagation time. Because if we're talking about a distance of 20 or 30 meters, divided by the speed of 2.4, then the actual propagation speed will be like 1 or 2 nanoseconds. So it's very low, and it can easily be ignored in that case. But here, this example talks about a very, very long distance transmission. Okay, so depending on the scenario, one of these components might be more significant. Okay, so here we talk about this particular scenario. So what is the propagation time and the transmission time for a 5 megabyte message? So the message now is long. The bandwidth is, instead of 1 gigabits per second, it's 1 megabits per second. So the bandwidth is reduced. So that talks about the scenario that I was just discussing. If we still have the long distance and the speed of transmission is 2.4, then the propagation time will stay the same because the two components are the same, but the transmission time now is higher. So depending on your scenario, the transmission time or the propagation time might be the predominant component, and in that case, you compare to 40 seconds, for example, which is not practical, of course, to take 40 seconds to transmit one packet. But if we assume that this is the case, compared to this, you can easily ignore 50 milliseconds, right? So you can, because it's 40.050, so it's nothing. So you can assume the total delay in that case is 40 seconds, and that's it. Okay. The last component that we will talk about, which is not typical to be used actually, which is what we call the bandwidth delay product. The bandwidth delay it's not something new. It's based on two things, based on the bandwidth and the delay, right? So this is combining the bandwidth and the delay. So if we were to combine the bandwidth and the delay and get the multiplication of these two components, what do we get? Well, let's see. We know that the delay that any bit will take is the delay from the start of the transmission until it becomes a signal over the line. So if one packet takes from here to here, like let's say 5 seconds or something, which is the time that the packet takes to be transmitted over the line and propagates to the receiver. Okay? So this is the delay, the total delay that the packet takes, or one bit will take from the start of the transmission until it goes all the way to the receiver. Okay? When we multiply this by the bandwidth, what do we get? When we multiply this by a bandwidth, remember that the delay is the total time in seconds or something. The delay is what? Delay is a number of bits per unit time. When we multiply the two, we get a bits. Okay? We get the number of bits. Okay? So what does this number of bits represent? This number of bits represent the number of bits that will stay on the line, okay, from the sender to the receiver. The number of bits that will fill the line. The number of bits that will fill this line. Why? Because this bit will take, let's say, 5 seconds. When we multiply it by the bandwidth, we actually measure how many bits can be sent over the line in this 5 seconds, right? So this is the bandwidth delay product. So what does this represent practically? This represents practically the fact that you have specific number of bits that will stay on the line all the time. And if this number of bits is really high, this means that the utilization of your transmission line is high. You have high utilization on the transmission medium, which means that your transmission medium is efficient because you have very high number of bits, okay, over this line at any point in time. If this number of bits is low, this means that the efficiency or the utilization of the line is not that high, okay? So we can, of course, so before that, of course, when we talk about full duplex, what does that mean? Do you remember what full duplex mean? So both the sender and the receiver, they can send to each other concurrently. So what does that tell you? This tells you that when you start sending from the transmitter to the receiver, also the receiver is sending you some bits, right? So when you calculate the number of bits on one direction, you multiply it by 2 to get the total number of bits on the two directions, right? So that's why for full duplex, the bandwidth delay product is actually 2 times the bandwidth times the delay. Why? Because it's bidirectional, and you have some bits going this way, some bits going this way, so you have to double the number of bits. So this tells you what? This tells you essentially that for full duplex, the utilization of the transmission medium is double, which is essentially, it's logical. We know that. So if we were to imagine what this bandwidth delay product means visually, we can assume that the transmission medium is actually a pipe. A pipe, okay? So the length of this pipe refers to the delay. The length of this pipe refers to the delay, which is the time that the packet will take from the start of the transmission all the way until it goes to the receiver. The bandwidth is actually the thickness or the size of the hole of this pipe. Okay, so in that case, the bandwidth delay product is simply the volume of that pipe. The volume of that pipe, which is the total number of bits that can fill this pipe. That's what it means. The total number of bits that can fill this pipe, which is actually the volume of the pipe. So visually, we can understand the metric of the bandwidth delay product. Which is measured simply as the number of bits, right? So it's the volume of this pipe.
Doctor, the number of bits that can be transmitted over the pipe is fixed, that we cannot send more than 20 bits. For example.
No, the number of is fixed.
Yeah.
It doesn't have to be fixed. Why? Because again, the delay, as we said, that this delay is variable in nature. So in practice, this delay might vary. The delay might vary because of what? Because of the queuing time. So at some point, you see that the number of bits that can fill the line is X. In another point, you will see it like 1.5X. So in that case, at that point in time, the utilization of the transmission medium is higher, is good, and that's sometimes because of the fact that the load on it is low. Okay, so it does vary from time to time. Okay. So any questions so far? Actually, in practice, however, we rarely use this metric. I mean, honestly, throughout my experience in data communication, we don't use that metric very often. So in reality, we see the throughput a lot. So we calculate the throughput, calculate the bandwidth, calculate the delay. These are very, very important metrics that we measure in practice, and it gives us good indication about the performance of the transmission. These are very, very important. And in addition to that, we have some other metrics from the application point of view that you probably will study if you were to take like multimedia networks or other courses. There are some other metrics that we care about, especially for multimedia streaming and these kind of things. But typically, delay, throughput, and bandwidth are the most important and the most frequently used metrics for performance evaluation. Any question? Okay. All right. So this was for talking about signals. This is the lowest level in the data communication system that we typically talk about. In chapter 4, we'll go one floor on top, and we'll start talking about digital transmission. We'll start talking about bits. So this is the first time we'll start talking about, officially, we'll start talking about bits. And in that chapter, we'll talk about how to convert bits into bits. And remember, when you studied 455, we talked about coding. So this chapter actually covers the coding techniques in details. Okay. So we'll talk about the purpose of coding. Why do we need to do coding for any stream of bits in the physical layer? So we're still in the physical layer. We went one step above. So if you remember, we kept telling you that in physical layer does two things, right? Coding and signaling, right? So we talked about signaling in the previous chapter. Now we'll talk about coding, because we are going from bottom up. So first we talked about signals, then we talk about coding, and then we'll go one step above to talk about data link layer issues. So, so in this chapter, we see how we can represent digital data by using digital signals. And in that case, we convert the data into some symbols represented by a digital signal. That this digital signal, we can later on, using the information that we studied in previous chapter, we can either transmit it using baseband transmission, right, using low frequency, or broadband transmission using higher frequency. So this conversion involves three techniques. Line coding. Line coding includes all the coding schemes that you talked about in 455, and in addition to that, some other techniques that we'll study in this chapter in details. So all what we have studied, all what you know about, which is basically the Manchester encoding and the non-return to zero, these are the two techniques that supposedly you have gone through in 455, and when we discussed the difference between these two, we'll see now that in line coding there are tons of other techniques that we can use for coding, and we call these line coding. Then we'll get to block coding. So we don't actually code bits like individually, but we code actually block of bits. And then we'll talk about scrambling. Scrambling معناه you take the bits and you scramble it, يعني تلخبطها. Okay? So we talk about the purpose of scrambling. Basically, all these techniques, they revolve around the fact that we need to make the digital bits that we generate at the end more error resistant. So the main purpose of line coding, block coding, and scrambling, all these categories of techniques, they try to make the bits that I transfer using either baseband or broadband, they try to make these digital signal and these digital bits more error resistant. And we'll see how this is achieved. Okay? So we'll talk about what the line coding means, and we'll talk about a series of line coding schemes and the difference between these line coding schemes. And we'll talk about some important metrics again with respect to this line coding schemes. Based on these metrics, we will say that, okay, this scheme is good from this perspective, but it's bad from other perspective. So we need to define some reference metrics based on which we say this scheme is good, this scheme is bad, and so on, right? Then we'll get to block coding, and then we'll talk about scrambling. So line coding basically talks about converting one data element. Why we say data element and we don't say bits? Because the data element could be actually 2 bits or could be 3 bits at a time. Okay? So we convert data element into a signal element. A signal element which is a digital signal that represents this data element. Okay? So in the previous chapter we talked about a stream of bits, and then we said that we can represent this stream of bits using one digital signal. So one data element represents one signal element represents one data element, and in that case we can convert or we can transmit this digital signal using one harmonic or 2 harmonics or 3 harmonics and so on, right? So here we know that we can use one signal element to represent 2 bits or 3 bits. Okay, so it's very important to get the ratio between the signal element and the data element, which is how many data elements can be represented by one signal element. So that's the example. So that shows this this concept. So you can use one bit to be represented by one data element. So a data element means a level of voltage, okay, a fixed level of voltage in one level, right? So this is one signal element, and this is one data element. So the ratio here is 1, simply. So here, this is a data element, and it can be represented by one signal element. Is there a way that we can represent one data element using 2 signal elements? Yes. What is the point? We'll see. We'll see how this could be actually useful. So this is the example here. So we can represent one data element using 2 signal elements. But we'll see why this could be useful or could be important, because logically we don't need to have this complicated signal to represent one data element. But when we study the line codings later on, you will see that in some cases this can have enormous benefits. Okay? So here the ratio between the number of data elements to the number of signal elements is half, 1/2. And this ratio is very important because it will help us later on to calculate so many things about this digital signal. We calculate what's very common is the baud rate. So you have dealt with baud rates at some point. So to calculate the baud rate, this is the ratio that we need to take into consideration. This example here talks about the reverse operation. So we can have 2 data elements represented by one signal element. Okay? So here the R is 2. Number of data elements is 2. Number of signal elements is 1. And it could be composite like this. And this is typically used for block coding, as we will see later. So you can have arbitrary number of data elements represented by arbitrary number of signal elements. So I can take group of bits and represent this group of bits using multiple levels of signal elements like this. And we'll talk about that later. So here, R is 4, which is the 4 data elements divided by 3, the number of signal elements. Okay? So R is very important to allow us to calculate what we call the baud rate or the signal rate. So this is the signal rate or the baud rate or pulse rate or modulation rate. All these are terms for the same thing, which is the number of changes in this signal. Okay, which is reflected on the bandwidth. So there is a direct relationship between this baud rate and the bandwidth of the signal. Okay. So S here is the number of signal elements. C is a case factor. This case factor is constant. And I have to give it to you. It's not something that you calculate. So this case factor allows you to measure the average baud rate. Because when you have a specific scheme, there is a worst case and there is a best case scenario. So the worst case scenario, for example, is when you have many changes in the generated signal. The best case scenario, or maybe you can reverse them. The best case scenario is when you have straight zeros and you represent that with a constant signal. So if you have a constant signal, the changes are a minimal or zero. If you have the worst case scenario, you have many changes. So C gives you sort of the average between those two extremes. Okay? So C gives you the average between. So the typical value for C is in many cases half, 1/2. So it's very important to calculate the value of R. So R is the ratio between the data elements and the number of data elements and the number of signal elements. So as an example, if the bit rate is 100 kilobits per second, so this is the bit rate. What is the average value of the baud rate? Okay, if C is between 0 and 1. Yes, we know that the worst case C is 1. In the best case C is 0. So we select something in between, which is a 1/2, and typically this is the value. And if we were to assume the simplest example, this is the simplest example. N is 100 kilobits per second, and C is half, which means that and R is 1. R is 1 meaning what? One data element corresponds to one signal element, which is the example that we talked about before. One of the simplest examples that we talked about before. A digital signal represented by one bit represented by one signal element. What is the baud rate here? It's C, which is 1/2, times N times R, which is 1. Do you remember what this relationship means in the previous chapter? This is typically so the baud rate here is represents the bandwidth, the minimum bandwidth that you can use to represent this type of digital signal. So the baud rate gives you, as I said, there is like a direct relationship between this baud rate and the bandwidth of the signal. Because again, this baud rate measures the changes in the digital signal that we can use to represent the data elements. Okay? Because as we said before, the minimum bandwidth is the bit rate divided by 2. Remember? We said that. So if we have one bit represented by one data element, so simply the bandwidth is the bit rate divided by 2, which is exactly what we have here. So if C equal to 1/2, then the baud rate is actually the bandwidth. Okay, واضحة? See here, the baud rate is measured as baud. We call it kilobaud or baud or something like this. All right, so we'll stop here and we'll take the. So the bandwidth, we know that the baud rate is measured as we said, there is a direct relationship between the baud rate and the bandwidth. So more information than the range of frequencies is needed. In addition, the amplitude for each component is an important issue, as we have studied before. So the bandwidth is, as we said, proportional to the signal baud rate or the baud rate. So the minimum bandwidth is typically what we have calculated as the baud rate or the average baud rate, given that this case factor is half. And based on that, if we have a specific bandwidth, as we have studied before, then we can calculate the maximum bit rate that we can accommodate using this bandwidth, right? So if we have a specific bit rate of the signal, we can measure the minimum bandwidth that we need to transfer this signal. If we have a specific bandwidth, then we can measure the maximum bit rate that we can get to transfer over this channel. So if this bandwidth here refers to the bandwidth of the channel. And this bit rate refers to the bit rate of the signal that we're trying to transmit. So by reversing the two, we can measure the maximum bit rate or the minimum bandwidth, right? طيب. This is a very important notion here, which is the effect of synchronization. So the effect of synchronization is very important, and it will affect our evaluation for all the line coding schemes that we will study later on. The synchronization is one of the very important factors. So the synchronization is based on the fact that the clock at the transmitter and at the receiver are rarely in sync to each other. There is always a clock drift between the transmitter and the receiver because they are two different devices, right? So we know that the clock even if the clock frequency is the same, there is always a possibility, and it's very high possibility in practice, that there is a slight drift in the clock of the receiver compared to the clock of the transmitter. So if this effect is there, then the sender sends a digital signal using a specific clock frequency, and here the clock allows me to get the boundary of each data element. Okay? So the boundary of each data element can be recognized based on the clock frequency. Okay? If the receiver is not in sync with the transmitter, this is what we will get. So here, the clock frequency is slightly more, which means that I will sort of recognize those 2 bits, I will recognize 1 bit boundary as 2 bits, right? Because the clocks are not aligned with each other. And this is very common in practice. Okay? So that's why some coding schemes that use fixed amplitude in one signal elements are not actually very prone to, are not very resistive to this synchronization. Why? Because if you have a change in the middle of the bit, okay, even if there is some clock drift, this change will give the receiver some information that, okay, so there is a change in the middle of the bit, so I'm in the middle of the bit now. So this will allow me as a receiver to adjust my clock to align perfectly with the transmitter if there is a change in the bit. But here in this example, there's no change, so there is nothing that will help the receiver to know that now I'm in the middle of the bit. I don't know, because there's one level fixed all over the signal element. So the signal element here is fixed, one level, right? So the receiver will have nothing to help him to recognize that now I'm in the middle of the bit, because there is one amplitude for the entire signal element. So that's why in some line schemes, some line blocking, some line coding schemes, if we use 2 amplitudes or 2 different levels, or in other words, 2 signal elements to represent one data element, this is usually very good for synchronization. So this reduces the effect of lack of synchronization between the transmitter and the receiver. ماشي؟ مفهومة كده؟ So if within one signal element we have a change of level, this will help the receiver to say, because we have this change, I'm in the middle of the bit. So even if I have some clock drift, I can adjust my clock to the middle of the bit. So I have some information to help me to resync. Okay, so that's why line coding schemes with 2 signal elements per 1 data element are very resistive to synchronization errors. ماشي? So an example that illustrates the effect of synchronization or lack of synchronization. So in a digital transmission, the receiver clock is 0.1%, 0.1% faster than the sender clock. So this means what? This means that for 100 bits or for 1,000 bits, I have 1 extra bit. How did I get that? 0.1% is 0.001, right? So we divide by 100. صح? So this means that I have 0.001 extra. So for each 1,000 bits, I have 1 extra bit at the receiver side. But regardless, if I have 1 extra bit for whatever number of bits, this means that the bits that I can recognize at the receiver are different from the transmitter. So in some applications, this can kill the entire application. Yani, imagine if you have a zip file. If you have a zip file, the zip file, if you change 1 bit in the middle, the entire zip file becomes unusable. صح? So there are some applications that cannot tolerate any kind of error. Well, this, if it happens in a video streaming application, I can live with that. But in some applications, they are very intolerant to error, any type of error, right? So in that case, this lack of synchronization between the transmitter and the receiver can cause even 1 bit every 1,000 bit to be different, and that's enough to make a big amount of error that will affect the communication. And in order for me to fix that, I have to do retransmission, and I hope that in the retransmission, the transmitter and the receiver will be in sync, and this problem will not happen. So, but that may happen with a very high possibility. So in any case, so if I have 0.1% difference or clock drift, so for each 1,000 bit, I have 1 extra bit. So at the receiver, what I will receive is actually, so if this is 1 kilobits per second, so I have 1.01 kilobits per second, or 1.001 kilobits per second. So any difference would cause a serious error, and that will affect the efficiency and the quality of the communication. Okay, so techniques with more than 1 signal element per data element can be resistive to this kind of problems, the missynchronization or the lack of synchronization between the transmitter and the receiver. So these are the metrics that I talked about. So we have very important definitions here. These are 3 different definitions that we will need to talk about. We'll spend some time on this, but I need to start with it next time so that it becomes solid in your mind. And this will be the base for us to evaluate any line coding scheme later on. We'll say that this is good for baseline wandering, but it's not necessarily good for DC component. This is good for self-synchronization, the example that we just talked about. If we have any line coding scheme with 2 signal elements per 1 data element, we know that this is resistive to the lack of synchronization. And the receiver, in that case, will have the good feature of self-synchronization. So this is what we talked about. The receiver will have self-synchronization. It has this change in the middle of the bit that will help the receiver to adjust the clock drift in case it happens. So we'll talk about these definitions next time, inshallah.